Hello everybody, myself Dr. Tajdarul Hassan Syed. I am an associate professor in the Department of Applied Geology, IIT ISM Dhanbad. In this module, today I will be presenting in front of you some of the basic concepts of hydrology and hydrogeology in particular. So with this, we would first like to understand the importance of water, because hydrology, as we know, is the science or the study of water in general. Now, from the childhood, we have been listening and hearing and reading in the books that water is a very, very important commodity in our life. And fortunately, on Earth, water is present in all the three phases, that is liquid, gaseous, and solid phase. And each of them has its own set of importances. For example, we have been hearing about liquid water because we know water is essential for our livelihood because we need it for drinking purposes. Water is important for agriculture, for industries, etc., etc. But we have to also understand that water in the form of vapor in the atmosphere plays a very, very important role also, such as regulating the temperature of the earth. How? Now, water is a very large component of the Earth's atmosphere, and we have to understand that water is one of the most dominant greenhouse gases that are present in the Earth's atmosphere. Now, why it is important? Because if we understand the greenhouse effect is basically something that some of the gases that are present in the Earth's atmosphere traps the terrestrial radiation from losing out from the surface. Now, where is this terrestrial radiation coming from? Since we know that the Earth is insulated by the solar radiation, that is the short wavelengths that are coming in through the atmosphere and touching the surface or heating the surface of the Earth. Now, what happens is after the Earth's surface gets heated, what happens? The Earth itself starts emitting radiations. Now, these are known as terrestrial radiations. Now, what is the difference between the solar radiation coming in towards from the sun to the earth and that which is coming out of the earth's surface is that a drastic difference in the wavelength. The solar radiation is mostly in short wavelength radiations, and in turn the earth's radiations are much longer wavelength, because we know that the radiation, the wavelength of the radiation that is emitted by a body is inversely proportional to the temperature. Now, with sun at having around about 6000 degrees Kelvin emits majority of its radiation within a very short wavelength of the visible range, or 0.4 to 0.7 micrometers. And on the contrary, the Earth's surface, which is generally on an average having a temperature about 300 degrees Kelvin, which is much, much lesser than the sun, is emitting at about 9.8 micrometers. So we can see that the wavelength of the terrestrial radiation, that is the radiation given out by the Earth's surface, is much, much longer. Now, what is the role of the greenhouse gases? The greenhouse gases has no impact on the short wavelength radiations. That means it allows the solar radiation to come or to pass through them and reach the surface of the Earth. However, it does not allow or traps the longer wavelength radiations. So we know that the terrestrial radiation, which are of longer wavelength, are basically trapped by the greenhouse gases. And so what happens is that the water vapor that is present in the Earth's atmosphere, having a huge greenhouse potential, it maintains the temperature of the Earth at a very habitable 27 degrees centigrade, or basically 300 degrees Kelvin. So we can see straight away that the water vapor that is present has an immense significance, apart from the fact that it is also plays a crucial role in the form of rainfall after it condenses. So we understand, and similarly, the water in the solid form, if we look at the snow and ice that are present, also plays a very important role by reflecting back solar radiation, which again keeps the Earth a little bit colder. So all these processes makes the Earth a very, very habitable place. Now, before we go on to the details, in this module, I'll just briefly introduce you, as I said, hydrology in general is the science of water, or the study which relates with water, and which includes basically the occurrence of water, the distribution of water, and the circulation of water from one place to the other. Now, if we come to the concept of hydrogeology, which can be considered as a part of the hydrology, here we deal only with water which is basically known as groundwater. Now, we have to understand one concept, that underground water, not everything or not all the water that is present underneath the surface of the earth can be called as groundwater. Why? Because if we look at the subsurface, the water is basically stored in the gaps or the pores that are present underneath within the unconsolidated or the consolidated rocks. So what we can see is that if we can draw a surface profile, if this is the surface, and we can see that if this is the surface of the earth, now we can see there are materials present underneath the surface. And what happens is that the water is basically present within the gaps that are present within the particles. Now, if we can draw a sort of a vertical profile, we can see that if we go down further below, what happens is that these pore spaces are initially filled up by water and air both. So we have water plus air within these pores. Now, as we go downwards, what we see is that the proportion of air and water starts changing. What happens is that as we go down below, we see that the pores are becoming saturated, more and more saturated with terms of water rather than air. So what happens is there comes a time where we see that the pores are entirely filled up with water. So this water, which is basically occurring within the saturated matrix or the saturated porous matrix, is what is known as groundwater. Everything above that saturated porous matrix, which is also known as the unsaturated zone, is basically known as soil moisture. So we can see, even though the soil moisture and the groundwater, they are defined as water which is present underneath the surface, there is a clear distinction because of where it occurs. Soil moisture occurs within the unsaturated zone, and groundwater is basically occurring within the saturated zone of the subsurface. So here, this is how we differentiate out between the surface water component, the subsurface component of soil moisture, and then there is the groundwater. So in continuation, I'll first talk about what is known as the hydrologic cycle. So we have been hearing about the hydrologic cycle right from our school days. So what is the hydrologic cycle? We say that this is the cycling of water from the land towards the atmosphere and to the ocean and then back. So this is the cycling of water. Now, if you look at the hydrologic cycle, there are two major components. One is known as the storage, and another is known as flux. So what is a storage? So when we talk about storage, here we are intending to represent the natural storages of water. For example, the land surface is a natural storage of water, a lake is a natural storage of water, and a river. So these are natural storages of water. So is the ocean and the atmosphere. So when we talk about the hydrologic cycle, we are talking about the different storages and fluxes that are present in the Earth system. Now, if we first talk about the storage, we have to understand that the land storage part is a very, very important component. Now, what do we mean by land storage? So if we look at the vertical cross section of the land surface, okay, we can roughly say that if this is the surface, then this is, sort of the vegetation. We can see there are different components of storage that are present below the surface of the earth, and we call this as, remember, soil moisture is one of the component of storage. Groundwater again is another component of storage. Similarly, there are storages above For example, surface water reservoirs, which we can draw something like this, surface water, which includes lakes, reservoirs, and rivers. And also we have to understand that there is the snow component which occurs, which is basically the snow and ice. So these are also forms of storages. So integrated, if we look at that, we can see there is on the surface or above the surface, there is surface water bodies which is storing water. There is snow and ice, again particularly in the higher latitudes, which is again a storage of water in the solid form. And then below the surface we have soil moisture, and then below that we have groundwater. So in total, if we can integrate this quantity, which is basically known as the terrestrial water storage. So terrestrial water storage is basically a sum total or the integration of the different storages that are available in the Earth system that is holding water. Now similarly, we can see that the atmosphere, is, if we consider atmosphere as a box, that also is a component of storage of water, and then we have the ocean also as a component of storage. So these are the major storages if we can consider. Again, there are finer classifications. Instead of going into that, let us now try to understand what are the fluxes. Now, what is a flux? Flux is basically movement of water from one storage component to the other. And there are different names given for each of these different fluxes, and which we have already faced in our common lives. For example, if we see the movement of water from the atmosphere to the ocean or to the land, basically we call that precipitation and precipitation or rainfall. Similarly, we have seen that water from the ocean and from the land surface moves towards the atmosphere in the vapor form, which we call as evaporation. Evaporation again is what is known as a flux. So in hydrology, what we do is that the fluxes are represented as arrows because they are representing a movement of water from one storage component to the other. And similarly, we can see there is another major component of flux, that is water that is running from the land towards the ocean, which is basically known as a runoff. So if we see a global picture, we can see that there are three main storage components. One is the land, another is the atmosphere, another is the ocean. And we can see here that the water is basically getting cycled like this. That means, water evaporates from the ocean, forms clouds, falls as rain, and then rain, some of the water percolates, some of them runs off into the ocean. Now, each of these components I'm going to explain what each of these components are and what is the state of knowledge of each of these different components. So let us start first with the component of evaporation. Now, what is evaporation? Evaporation is the process in which the liquid water gets changed into the vapor phase. Now, for evaporation to take place, we need to introduce some definitions or some words that is of high importance. One such important word, terminology is known as the saturation humidity. So, what is the saturation humidity? So, if we look at a parcel of air has a capacity to hold water vapor or to hold moisture. At a particular temperature, the maximum, the amount of moisture or vapor it can hold is known as the saturation humidity. Now, what happens is generally the amount of moisture that is present in the air is less than that of the saturation humidity. And another case which is very well defines this relative difference is known as relative humidity. Now, this is a very common term we often hear. What is the relative humidity? Relative humidity is the ratio of the water vapor that is present in the air at a particular temperature divided by the maximum amount of moisture it can hold at that particular temperature. Generally, we represent that as a percentage. So what happens is that whenever we say a relative humidity is 100%, it means that the air is holding water at its maximum capacity. Now the process of evaporation only takes place when the saturated relative humidity is less than 100%. The moment the relative humidity reaches 100%, evaporation ceases. Okay? And we have to understand this. As I said, why am I stressing on a particular temperature is because the saturation humidity of an air parcel actually increases exponentially with temperature. So if the temperature increases, that means the water holding capacity of the air also increases. Okay? So what we are saying is that if the relative humidity is less than that of the if the relative humidity is less than 100%, there is the process of evaporation going on. Now, this is evaporation. Another component which is very, very important, in which also we see that water in the liquid form is getting transformed into a vapor phase, is known as transpiration, which is a process initiated by the plants on the surface of the earth. So what happens is that these plants, through their roots, they take up water from the subsurface, and then basically it transpires in the form of vapor and it goes again to the atmosphere. So this is a flux which is moving in the direction towards the atmosphere. Together, these two terms, evaporation and transpiration, is very commonly known as evapotranspiration. So we often use the term together, evapotranspiration. So evapotranspiration, if we look at, is a process which is occurring on the surface of the earth. Why? Because the earth's surface has water with free surface, that means lakes, reservoirs, rivers, and also it has plants which basically transpires. So when we are drawing the flux from the land surface towards the atmosphere, we conveniently use the term ET or evapotranspiration. But in the case of ocean, see, I have written evaporation, not evapotranspiration, because there is no plants which is transpiring water. So evapotranspiration is a very, very huge important flux, but the measurement is actually very, very difficult, owing to the heterogeneity in the plants. And by the heterogeneity in the plants, I mean there are the various different plants transpire at different rates. Evapotranspiration is a significant flux in the hydrologic cycle. But the thing is that it is relatively difficult to measure. In open air or in open water surface, evaporation is relatively easier to measure compared to that of evapotranspiration. This is owing to the fact that this depends on various different factors, which includes different types of plants, because each and every plant transpire at different rates. So there are now people are working on eddy flux towers, which is one of the way they measure, and now some of the techniques have been developed to measure evapotranspiration using satellite-based measurements. Now I come to the second component, which is known as precipitation. Precipitation is a very common phenomena we encounter in our daily lives. Now, when does this precipitation occur? As I said, that when the relative humidity exceeds 100%, the vapor starts condensing. Now, how does it occur? Now, how does it reaches 100% relative humidity is that if we reduce the temperature of the air parcel, what happens is that the saturation humidity starts decreasing. And once the saturated humidity starts decreasing, the relative humidity starts increasing. So the basic process what is required for the process of precipitation to take place is that we need to cool the air parcel. And that is done by raising the parcel of air towards a higher altitude in the atmospheric column, because the temperature, as we know, in the lower parts of the atmosphere decreases with height. Now there are three major natural processes by which air is lifted and condensation can occur, and based on that there are three different types of precipitation. One precipitation type is known as convective type of precipitation, which is basically convective type of precipitation. Another orographic, and the third is frontal. So these are the three different types of precipitation that occurs. Convective, as we know, that when the land surface gets heated, the air surrounding the land surface or near the land surface becomes warmer, so it starts rising in the atmospheric column. This is a way we know that the condensation can take place. Another is orographic. That means it is related to do with the topography of the surface. That means what happens is sometimes the air parcel hits the side of a mountain or a higher elevation, then the air is forced to rise. So because of that, again, condensation takes place. And the third type, which is known as the frontal precipitation, this occurs when two different air masses, one very warm and light, another is very cold and dry, they meet with each other. Then what happens is that the colder air, which is basically denser, slides underneath the warmer air and it is pushed up, so that the warmer air, which is having more moisture, is forced to rise, so the condensation starts to occur. Now, for the actual rainfall to occur, we have to understand that just by raising the air parcel, the rainfall would not be able to take place, because for condensation we need a substrate or an object over which the condensation can take place. So one of the most important component for rainfall to occur is a nuclei on which the condensation can take place. This nuclei is also known as CCN, which stands for cloud condensation nuclei. So what are these? These are very, very fine dust particles, dirt particles, aerosols that are present in the atmosphere. So we can see that for rainfall to occur, we need the air parcel to rise, and not only that, we need to have CCN, which stands for cloud condensation nuclei, to be present in the atmosphere, so that condensation can take place on the nuclei or the substrate. Regarding the measurement of precipitation, again, amongst all these fluxes, we have a very good confidence on the amount of rainfall that is measured. On the ground, it is measured by something which is called a rain gauge, and nowadays almost each and every airport has a rain gauge. And apart from that, major precipitation data or the amount of rainfall that is taking place can be very well measured by the satellite missions that are present. There are also future satellite missions coming up in just to measure the precipitation. So although we have a lot of confidence in today's context about the amount of rainfall that is occurring, but still it needs much more refinement. Now, the final component, which is known as the runoff. So now we have to understand that when rainfall occurs, so we saw that water is evaporating, it's condensing, and then it falls as rain. Now when the rainfall reaches the surface of the earth, the first thing that occurs is that a part of the amount of rainfall percolates or infiltrates into the ground. So we can see that rain, when it occurs, some part of it is infiltrating into the ground surface. And the rest of it, what happens is once this surface layer becomes saturated, it starts flowing laterally on the surface of the earth, which is also known as overland flow. Now subsequently what happens, in which direction the water is moving is basically, as we know, basically it's gravity driven, so it's moving towards the points of lower and lower elevation. So finally this overland flow, or the excess of water that is on the surface, runs towards the streams and channels, which again joins major rivers, and finally it reaches out into the ocean. Now, how is runoff or river discharge, as we can call it also, is measured? There are different types of velocity meters or flow meters, and also we measure by the stage or the height of the river channel. So the height of the river channel is used in something called a stage discharge relationship, by which the height of the river is converted into a volume, so we know the amount of volume that is water is moving towards the ocean. Nowadays, satellites are also playing a very important role in trying to measure the stage of a river, which can again be converted into a volume, so we know the amount of water is moving. But again, we have to understand that things are not so easy as it seems on the blackboard, because river channels, as we know, they are constantly moving, they are constantly bifurcating. So what happens is it's not like that the entire water is flowing through a particular channel and it is constant. So it is shifting, some of the channels are braided, and then finally when it reaches into the ocean, there are numerous channels which are bifurcating from the main channel. So again, it's very, very difficult to measure the total amount of water that is falling on the land and that is running towards the ocean. So there is an active area of research going on how to quantify the volume of water that is reaching into the ocean. So finally, I'm going to conclude the model by briefly talking about what is known as the water budget equation. So this is a very common equation which is used by hydrologists. This equation states that the changes in storage, if the S stands for storage, is equals to inflows minus outflows. So on the left hand side, we have a change in storage. That means how much of volume of water is changing, and by storage is the storage of any component or any control volume you can think of. We can consider the entire land surface as a control volume. We can consider it as a river basin as the control volume. And on the right hand side, it says the inflows and outflows of water. That means what are the fluxes of water that is coming into the control volume and what are the fluxes of water that is going out of the control volume. So now if I take an example of a river basin, so for example if I draw a river basin very roughly, and here we are saying that these are the streams in the river basin. So if I can write the equation for a case of a river basin, I can see that what are the major inflows. The main flows is basically, as we know, precipitation is the major inflow. And what is an outflow? Again, evapotranspiration, as we saw, which is the transfer of water from the land surface towards the atmosphere, is again an outflow. As we can see that the arrows indicating going towards the basin is an inflow, out of the basin is an outflow. Another outflow is a runoff, as we have discussed earlier, and there can also be some lateral flow of groundwater that is taking place if GW stands for groundwater. So there can be groundwater inflow and also there can be groundwater outflow. So what we are saying is that if I want to write the water budget equation of a river basin, I can say that delta S is equals to P minus evapotranspiration minus runoff plus groundwater inflow minus groundwater outflow. So here, as we can see, this water budget equation, or the balance of equation, is known as the water budget equation for a river basin. But we have to keep in mind that the fluxes that we are writing on the right hand side is not constant, because it is going to change depending on what is the control volume, and also we have to understand that some of the fluxes are dependent on the climatic condition or the geography of where the control volume actually is located. So I would like to summarize by saying that in this module we briefly talked about the importance of water, and we saw there are two major concepts that we discussed here. One is the hydrologic cycle, and again, even though the diagram we have drawn is very simplistic, we have to understand that the diagrams are much more complicated when we try to put numbers into it. So here we just simply drew boxes and arrows, but the diagram is only going to be complete when we are able to put numbers into those arrows. So a significant effort of the hydrology community is going into putting numbers on understanding what are the errors in those fluxes and storage values. And again, the water budget concept, as we can see here, is very commonly used, and sometimes it is used also not just to understand the changes in storage, but sometimes this equation is rearranged in order to find out some of the difficult to measure fluxes, something like evapotranspiration and runoff. So thank you all for paying attention. Thank you very much.